In this lesson, I'll show you how to find the absolute maximum, minimum using partial derivatives. This time the question reads, find the absolute minima and maxima of the function f at xy is equal to 48xy minus 32x cubed minus 24y squared on the region x is between 0 and 1 and y is between 0 and 1. I want to start with a visual, and I want to show you what this looks like on an xy plane. So here's the y-axis, here's the x-axis, and between 0 and 1 is from here to here. So that's 0, that's 1. And from 0 to 1 on the vertical is from here to here. So that's 1, 0. Therefore, what we have here is a square. I'm going to call this L1, L2, L3, and L4. You'll realize the significance of these in a few minutes. Next, I want to find the critical point of this multivariable function, and I can do that by finding the partial derivative with respect to x, setting that equal to 0, then with respect to y, setting that equal to 0. Then you have a system of equations which you can solve simultaneously. So starting with this, we have this term becoming 48y. This term becomes 32 times 3, using the power rule, that's 96, x to the power of 2, and that's a constant, it becomes 0. And we'll set this equal to 0. Now the partial derivative with respect to y, that becomes 48x, because we're holding x constant this time. And finding the derivative of y is 1. That's a constant, it becomes a 0, and that becomes negative 48y to the power of 1. And we'll set that equal to 0. Now we have to solve these two equations simultaneously, like a system of equations. I'll start with the bottom one because it looks like the simpler of the two. And I'll factor out a 48 from these two terms. I get 48 bracket x minus y. Dividing out both sides by 48, the 48 factor goes away, leaving me with x minus y is equal to 0, bringing that y term over, y is equal to x, and vice versa. Next, I will substitute the content of x, which is y, into here. I end up with 48y minus 96 y to the power of 2 is equal to 0. That is a quadratic, an incomplete quadratic, which you can solve by factoring. Factoring out a 48 from both of these terms, because that's a common factor, and a y, we get 1 minus 2y is equal to 0. Setting this factor equal to 0, we have y is equal to 0. That's one of the coordinates of our critical points. And setting that equal to 0, I get 1 minus 2y is equal to 0, bringing that over. 1 is equal to 2y. Dividing both sides by 2, we have 1 over 2 as another y coordinate. Substituting this into there and substituting that into there, I get two critical points at 0 and 0 and half and half. Unlike in question number 1, our critical points actually fit within this region. Therefore, you have to now evaluate the function at these critical points and get an output, because that could potentially be a minimum or a maximum. Substituting 0 into your function, all three terms become 0. So the output, if you substitute that into f, is 0. And the output, if you substitute halves into f, you get 2. And in case you're curious, the calculation is shown on your calculator. So this is a potential minimum, and that's a potential maximum so far. Now we have to find out what happens along L1, L2, L3, and L4. We did this in question number 1, so if you watched question number 1, this should be familiar to you by now. Starting with L1 region, our function, don't forget it, was, and we'll evaluate this at our function where x is unknown, because it can be anything between 0 and 1, but we know what y is, it's 0. So let's substitute those in. This becomes 0, that becomes negative 32x cubed, and that also becomes 0. Next, we'll evaluate this equation when x is equal to 0 and x is equal to 1, because notice that our bounds are between 0 and 1. Placing 0 into there, you end up with 0 as your output. And substituting x is equal to 1 into there, you end up with negative 32. So this is a potential new minimum, absolute minimum. Let's try L2. The same equation that we started with, let's rewrite it. And this time, we know our x, it's 1, but y can be anything between 0 and 1. Therefore, substituting 1 into here, we get 48y. Substituting 1 into there, we get negative 32. And here we have negative 24y squared. We can substitute, of course, y is equal to 0 and y is equal to 1, but you also have to substitute, given that this is a quadratic, any critical points. So we need to find the critical points using the closed interval method. We take the derivative of each of these terms. This becomes 48, that becomes 0, and this becomes negative 48y. Set that equal to 0. We get y is equal to 1. Y is equal to 1 is one of the points that we're evaluating anyway, so ignore this. But you still have to do this test if you have a quadratic. Now you're probably wondering that this was a cubic, why didn't we do it there? Because if you find the critical points of this function, it's 0, and that's why I didn't prove it. So substituting 0, this becomes a 0, that becomes a 0, we end up with negative 32 again. And substituting 1, that becomes 48. 48 minus 32, 16. Substituting 1 into there, we have 16 minus 24, that's negative 8. So still nothing new here. Our potential minimum is negative 32, and our potential maximum is 2. Once again, there's the function we started with, and this time x can be anything between 0 and 1. Y has to be 1. Substituting x and y, we get 48x. Over here we get negative 32x cubed, and over here we get negative 24. This function is slightly more complicated than the previous one, but that's fine. We need to evaluate this when x is between 0 and 1. Also, we need to find critical points. We can do that by taking the derivative of each term and setting the whole function equal to 0. Now, let's solve for x in this equation. Bringing the negative 96 over, I have 48 is equal to 96x squared. Divide both sides by 48. This becomes a 1, that becomes a 2. We have 1 over 2. And square rooting that, we have these x values as well. So it's a lot more work. Let's start with 0. If I substitute 0, I get negative 24. Still negative 32 is the minimum. Substituting 1 is the same thing as before, remember? Where we got negative 8. And now substituting the square root of a half, for that I'll use my calculator to expedite the process. The square root of 0.5, approximately negative 1.37. So here we should get negative 1.37. That was a complete waste of time because still negative 32 is the absolute minimum. Finally, for L4, rather than rewriting the function again, I'll just pretend that this is 0 and this is y. So for L4, we have a function. This becomes a 0, that becomes a 0, and that becomes negative 24y squared. We have to evaluate this when y is equal to 0 and when y is equal to 1. Substituting this, when y is equal to 0, we get 0, and substituting 1 into here, we get negative 24. So we have to look at all of these outputs for L1 to L4 and the critical points. Do you remember these? And as you can see, when the critical point at half and half, you ended up with 2. That was the highest value out of everything we calculated. So that is our absolute maximum, and it occurred at this point. The absolute minimum occurs at x is equal to 1 and 0, and that's negative 32. And we also found it when we had x was equal to 1 and 0, which is consistent actually. So we can conclude that our absolute max is at 2 and our absolute min, that's an x, is at negative 32. And there you have it. That is how to find the absolute maximum, minimum using partial derivatives.